Welcome everybody back to Python Web Conference 2021. My next presenter is a good friend of mine, Meredydd Luff from the Anvil project, and I'm so excited to have him back this year. He's a alumni now of our speaking crew, and I'm looking forward to this talk as well because I've not seen it yet. So I'll let him dive right in. Don't forget, afterwards there will be the face-to-face room down below. Click on that and you can actually join us to talk to Meredydd and have discussions face-to-face with other presenters. I'll be watching the Slido and I'll be watching the Track Slack channel for other questions. And if there are any, I'll make sure I interject them when appropriate. I'll let you take it away.
All right. So thank you very much. Always great to be here. I was saying just before coming back to Python WebConf definitely feels like being back among friends. So if you don't know me, my name is Meredydd. I co-founded and run a company called Anvil, and today I'm going to be talking about a topic near and dear to my heart, which is abstractions in programming. We're going to talk about what they are, why they're great, how they can go wrong, and what we as programmers, as professional creators of abstraction, can do about it. And then I'm going to walk through a few examples along the way and some more in-depth examples from Anvil, our platform for building web front ends and back ends with nothing but Python, which, as you'll see later, has a lot of abstraction-related challenges that I'm looking forward to walking you through. So, oh dear, of course. What's an abstraction? An abstraction is a model. It's a way of taking a difficult or complicated underlying system and creating an easier or simpler model and interacting with that instead. Here's an example. As far as your computer is concerned, your hard disk is a fixed length array of bytes, a few billion or trillion of them. It can read the bytes at a particular position in that array, and it can update what bytes are stored in a particular position in that array. And that's really about it. This is not a great interface to program against, so instead our operating systems provide an abstraction of files and folders. So instead of manipulating this big byte array, I can manipulate files with names and attributes and permissions and organize them into folders, and I can shrink them and grow them. And it is the operating system's responsibility, when I append 10 megabytes to a file, to decide where in that big array of storage to put that data, and to maintain the bookkeeping so that when I come back and read that file, it's presented to me as a linear array of bytes, no matter where across that disk it's stored. This is a great and productive abstraction, and we all use it every day. Here's another example. So your computer's processor understands a very limited set of instructions. They are like about 32 bits long each. They're mostly integer arithmetic and reading and writing bytes from specific addresses in RAM. You can assemble this machine code directly by flipping bits if you want to, but that's not very ergonomic. More likely, you would write it in assembly, which it looks like a programming language. It's mostly a mnemonic. Each line of this corresponds directly to an instruction that the CPU understands natively. It's really just another way of phrasing machine code. This, again, isn't actually a very productive environment to program against, and so we create abstractions. Here's an abstraction that you might be familiar with. It is, of course, Python, which allows us to write programs at high levels and much more symbolically, and is generally more fun to use. This abstraction is provided by the Python interpreter, and it is the interpreter's responsibility to run programs that are written like that on a processor that only understands instructions like this. And that That is its job. That is the abstraction that is the Python programming language. And abstractions are great. They really are the bee's knees. They are why we can have nice things in computing. You may have heard of the famous saying attributed to David Wheeler, an early giant of the field here in Cambridge, that every problem in computer science can be solved with another layer of abstraction. In fact, I'd say this is the thing that makes us as programmers different from other sorts of engineering, because our day-to-day work is creating new abstractions. We do it when we create libraries and frameworks. Stripe is an abstraction over dealing with credit cards. Pandas is an abstraction over dealing with tabular data. But we do it at small scale all the time. Every time we write a Python module with a set of functions that will be imported elsewhere in the same code base, we're building a little abstraction to do whatever it is we do. Abstractions are what we do as a profession. And that is important because abstractions bite. Abstractions can go wrong in ways that cause significant pain to the users of your abstractions, that is, other programmers. And so I'm going to walk through a couple of big ways that they can break. First, an abstraction can leak. And what I mean by that is that the underlying details of the system the abstraction's modeling, remember the abstraction is a model of some underlying system, the details of that underlying system or the details of how the abstraction is implemented can become uncomfortably relevant to the user of the abstraction, and suddenly they need to understand the underlying system you are shielding them from, or they need to understand how you built the insides of your abstraction in order to get anything done. Here's an example from Python. So if you write a class in Python, you can give it a method called dunderdel. And that method will be called when the object is destroyed. So if you use your object in a simple function, that object was created on the first line of function x, and the finalizer will be called at the end as you return from that function. You could use this to clean up some resources associated with your object. The problem is it only mostly gets called there. The actual rules for when your finalizer gets called are very complicated and depend on the details of how the Python interpreter manages memory, which is to say, it depends on the details of how the interpreter implements that abstraction of, of objects on top of the underlying system of bytes in memory. And so the details of that abstraction leak through, because if you use finalizers, you have to understand the rules for that, which means you have to understand implementation of interpreters. And that is why we don't generally recommend using finalizers in modern Python, because it's a very leaky abstraction. Here's another example, Sql Alchemy, which is a library for automatically translating between rows in an SQL database and Python objects. It's great. It means that instead of having to write code in another programming language, which is essentially what SQL is, here's an example, you can instead write your queries as Python expressions. So here we are, querying books and filtering for book.price is less than 20. Now, this is nice, but the process that turns that Python expression into SQL we can execute against a database is black magic. We are talking metaclasses. We are talking overloading innocent operators to do something completely different to what they normally do. And if you poke it too hard, you'll discover that. If you start writing code that assumes that book.price is less than 20 is an ordinary numerical comparison, you'll come unstuck. And you'll have to learn that actually, no, that's an overloaded less than operator that returns an intermediate object that SQL Alchemy then uses to generate source code in a different programming language. And so in practice, to use this effectively, you need to understand Python, and you need to understand SQL, and you need to understand how SQL Alchemy does that translation. So this is a very leaky abstraction. Not to say it's worthless, but it's very leaky. You need to understand how the sausage is made. So what can we do when when an abstraction leaks? There are many, pieces of advice. This is essentially a design question in software. What can we do when it leaks to avoid our abstractions leaking, to make them more pleasant when they leak? But I think some of the best advice is in a possibly unusual place. It's PEP 20, the Zen of Python. If you're not familiar with it, this is a set of sayings among the Python community. If you've ever heard simple is better than complex, or there should be one and only one way to do it, that's the Zen of Python you're hearing quoted. And although it is the philosophy of the Python programming language, what it really is a guide to building good abstractions. So let me go through a few famous ones. Simple is better than complex. Why is simple better than complex? Because when you're building an abstraction, you're building a new model out of whole cloth. And the user of your abstraction is going to have to wrap their head around this new model you've created. And the simpler it is, the easier it is for them to do that. And remember, everybody's day-to-day job is creating and using new abstractions. So the simpler yours is, the easier your users will find it to get on with their job. Simple is better than complex. Explicit is better than implicit. What does this mean? Let's go back to our finalizer example from earlier. So here, where we define an instance of my class, and then we do some work, and the finalizer automatically cleans itself up at the end of the function. The call to the finalizer is implicit. It kind of happens automatically, and you have to understand a bunch of rules to know that that will happen. This is it opens you to leaks of the abstraction because you have to understand what the rules are, and those rules are informed by the implementation of the interpreter. But it's also difficult to understand. It's not very Pythonic. Here is an example of the Pythonic way to do it. Instead of using finalizers, the recommended way would be to make my class a context manager and use it in a with statement. Now, it's plenty clear when the cleanup code runs. It runs right there because we have made it explicit. And so an abstraction where that stuff is explicit is an abstraction that's less likely to leak. If the implementation is hard to explain, it's a bad idea. Now, why is that? Well, if and when your abstraction leaks and starts leaking its implementation details, your poor user is going to have to understand how you built it. And if your implementation is hard to understand, they're going to have a hard time doing that. If it's easy to understand, then actually your abstraction leaking doesn't hurt them so much. So we can use rules and guidelines like the Zen of Python to help us build abstractions that are less likely to leak and less damaging when they do leak. And this is great, but it is a truth of software engineering that abstractions do leak. If you use the React web framework for an extended period of time, you will end up knowing quite a lot about how a web browser modifies its DOM and how React updates DOM objects in the web browser, because the abstraction will leak. If you use SQL Alchemy for long enough, you will need to know Python and SQL and how exactly SQL Alchemy does that transformation. It's a little bit rude. We should avoid doing it if we can, but it's not the end of the world. It might not be what your user plans to do with their day, but they can just learn about the underlying system. Abstractions can do much worse than leak. They can fail outright. When an abstraction fails, by that I mean the underlying system can do something, and the user needs to do it, and the abstraction prevents the user from doing the thing that they need, which is possible. And at this point, the user is cursing your name to the 7th generation because your abstraction has just prevented them from doing their job. Now, what happens when an abstraction fails depends on how the abstraction is built. And depending on how the abstraction is built, there are about 3 ways this could go down. To take the first one, let me take you back to the heady days of 1998. Imagine that you have a popular and profitable application. And because it's 1998, that means it's built as a Windows desktop application. But now your customers are coming to you and saying, can I use this thing on this newfangled World Wide Web? And you're in trouble because the answer is no. You have built your application on the abstraction of a desktop GUI toolkit. And that abstraction can't do that thing your customers are asking for. You are going down with the ship. Your only choices are to do a very heavy rewrite to get yourself out of that abstraction, or to say, sorry, that's not a thing we can do, and hope the requirement wasn't that important to begin with. This did not end very well for companies that chose option B in the late 90s. So as authors of abstractions, this is a thing that we really want to avoid. So let me tell you about one that does it a little bit better. Create React App. If you're not familiar with the front-end web ecosystem, these days you don't just have to write a bunch of HTML and some CSS and some JavaScript to build a web application. You actually write that, and then you assemble your application with a build chain that involves minifiers and CSS preprocessors, and all coordinated by a central build tool, usually Webpack. And this is actually quite complex to configure. And indeed, this is what I got when I first Googled Webpack config file. It doesn't even fit on one slide, and this is a simple example. So this is obviously a little bit forbidding for setting up a new web application, and so Facebook created Create React App, which is an abstraction over all of this that lets you say, create me a new application, and it will set up all of this as a template. What's more, it will then provide much simpler configuration to you, so that you can say, you can configure your build chain, your packages, and so on, without having to get up to the elbows in configuration for Webpack and your minifiers and so on. However, it is reasonably likely that you will find yourself needing to do something that Create React App doesn't support. And there is good news here, because although your abstraction has failed, the developers of Create React App have provided a better alternative. You can call Create React App --eject. And it will write out all of your configuration as the full configuration for all the front-end build tools. At which point, you can go in and do whatever advanced thing you needed, because you don't need to rewrite your whole build configuration. You haven't gone down with the ship. You can just eject, modify the configuration, do what you need, and get on with your job. So that's good. But the downside is that you've ejected. Your abstraction is gone. You needed one advanced feature, and they've left you in the middle of the Mojave Desert with a parachute, a survival pack, and a copy of the Webpack manual. It's a little bit rude. And so if we could do something better than this, that would be great. And as an example of that, let me talk about numerical computation in Python. One of the downsides of the way that Python is implemented is that arithmetic is pretty slow in Python. And therefore, you can't really do serious numerical programming in Python itself. You would have to use a lower level compiled language, something more like C or Fortran. Now, you could imagine a world in which, when that abstraction fails, Python offers you an ejector seed. You could call Python --eject, and it would go through all of your .py files and translate them to C. At which point you have a C program, you can compile it, you can build it, and then you can go and modify it to do whatever add whatever numerical code you needed, import whatever numerical libraries you needed, and get on with your job. Of course, that would be very unpleasant because you then couldn't write your application in Python anymore, and you would lose out on everything that abstraction was giving you. So what Python offers is something better than that. What it offers is an escape hatch in the form of native extensions. So a native extension is a way you can build using a low-level language like C, and you can provide hooks and then import that code into the Python interpreter. And so your C program can define modules and functions and classes that you can then use from Python. And now you can write your numerical code in C, escape the abstraction, climb out of your escape hatch, do what you need to do, and then climb right back in and write the rest of your code in Python. This is how all the libraries you probably thought of when I said numerical programming work. That's how NumPy and SciPy and TensorFlow and PyTorch all work. And so actually, Python's moment is driven by effective use of this escape hatch. These are clearly what we want. Escape hatches are the best way to cope with an abstraction failing. And so this, as abstraction authors, is what we want to build. Now, if this were a 25-minute talk, I could leave it there and everyone could go home feeling happy. But this is Python WebConf, and so we have to talk about the web. And I say that gingerly because what I'm about to do is consider the web as a programming platform, which is to say, as a set of abstractions. If we look at this, look at a web application from the perspective of our data. Our data will probably start out as rows in an SQL database, accessed by the SQL language. But of course, the first thing we're going to do with it is turn it into Python objects, which are accessed by methods and attributes that we've defined. We will then immediately turn around and render those objects as JSON on HTTP endpoints accessed by this weirdly limited set of verbs like get, post, put, delete. But at the other end of that HTTP connection, in a typical web app, is some JavaScript that will be reassembling those payloads into JavaScript objects with their own attributes and methods, and then turn around and render those JavaScript objects as HTML DOM for your browser, which you'll then use CSS to style into pixels, and that is a lot of representations of your data. The day-to-day work of a web programmer is mostly translating your data between those representations with a bit of business logic mixed in. And because that work is tedious and repetitive, we as programmers, we don't like tedium. We have invented abstractions to help us. We've already met one of them. It's an ORM, like Sql Alchemy. That's an abstraction that helps automate the translation between rows in a database table and Python objects. The problem, as we've seen with that abstraction, is that it's very leaky. To use it properly, we need to understand Python and SQL and how SQL Alchemy does the transformation. And we might be able to get away with that once. But of course, that's not the only framework in our stack. We've got ORMs like SQL Alchemy helping us turn database tables into objects. We've got REST frameworks helping us expose those objects on HTTP endpoints. We've got JavaScript frameworks like Angular's resources helping us reassemble those HTTP payloads into JavaScript objects. We've got templating engines like React helping us turn those objects into HTML DOM, and we have CSS frameworks helping us render those into pixels. And that's a lot of abstractions. What's worse is that they're all bridging really difficult gaps in representation. And so they all have the same problem as SQL Alchemy, which is that they are abusing the semantics of one layer, like Python, to represent a different layer, like SQL, a whole different programming language. And so all of these abstractions are terribly leaky, which has the effect that you need to know about everything in every one of all of these boxes in order to get your work done as a web developer. Every problem in computer science may be soluble by another layer of abstraction, except for the problem of having too many layers of abstraction. So we looked at this and thought, okay, how could we do better here? Because if you take this and you just build a new and better JavaScript framework, you're not going to solve the problem because you need to know everything else in all the other boxes. There are too many abstractions and they all leak too much. So we decided by building Anvil to replace this set of abstractions with one, and one that would stay coherent. And the one we chose was the Python language. So instead of this stack of frameworks, we built a GUI toolkit in Python with a drag and drop designer for it that represents UI components as Python objects. We used a Python to JavaScript compiler so that you can write your front-end code in Python and run it in the web browser. So instead, when you are driving your user interface, instead of manipulating HTML DOM, you're just changing attributes on Python objects. The server side is Python code, obviously, but when you've got Python on the server and Python in the client, then you don't need to mash all of your data into JSON and REST endpoints. You can just make a function call. And we even built a Python object-shaped database layer so that you can pass rows from your database all the way from the data store to the code that's driving your UI without changing its representation, which means without changing the abstraction you're using. So that's the theory. Let me show you what that looks like in practice. So here is the Anvil Editor, and I'm going to show you what we've done by building an quick example application. So I'm creating a new application, and here I am in the editor. This here is a web page, and this is a toolbox of things I can put onto that web page. So I'm just going to build a Hello World app. It's going to have a card. It's going to have some text on it. It's going to prompt the user to enter their name. I'm going to add a text box so that they can answer that question. And I'm going to call it name box. Every component in Anvil has a variable name, so we can access it from Python. I'm going to add a button so they can signal when they've answered that question. Make it a bit more prominent. And you can see what's going to happen. They're going to enter their name, click the button, and a message is going to appear. So here's the label that message is going to appear on. And we can make it centered and make the font big and so on. So we've just built a UI on the web. So what? Well, the important thing is that this is all backed by Python. So if I double click this button, I'm now editing the Python code that runs when this button gets clicked. And all of those UI elements I dragged onto my page are available as Python objects, which means that if I want to update the message based on what name they put in the name box, I can go self.messageLabel.text equals hello self.namebox.text. So I can run this now. And what do you know? We've built an interactive web app with nothing but Python. I'm actually going to publish this online now. So hello PWC. OK, you can now go to hello-pwc.anvil.app and see this application live online. It really was that fast. So let's look at the abstractions we've built here, because to do this with a classic web stack, you would have needed a bunch of HTML and CSS and JavaScript to drive them all. Whereas here, everything is still a Python object. We've dragged and dropped some Python objects as UI components, and we've accessed them from Python code, and we haven't had to bridge between two difficult to combine abstractions. Of course, any serious application is going to need some server code, so let's add a server module. This is a Python module that runs on the server. It's hosted by us by default. I'm just writing an ordinary Python function. Now I can tag this function as anvil.server.callable. And what that means is that I can call this function on the server from the client. So here, when the button gets clicked, I update my UI, but I also anvil.server.call, say hello, and then I pass in the text from that text box. And again, see that we haven't actually changed you haven't changed the form in which this data is represented. It's all just a Python function call. It's just a Python string. And sure enough, we can see there's some output in the logs here. That function has run on the server. So now we're really in business because we can use all the modules that Python has to offer. This is compiled to JavaScript. This is full-on CPython. Let's just tie this together with the database. So I just added our data tables, our Python-shaped database object. It's backed by Postgres, so I can stick terabytes into this thing if I want to. I'm going to be a little bit less ambitious and record all the names and the dates of arrival of all of these visitors. And again, everything here is a Python object. This is apptables.visitors. So I can go to my server code and I can go apptables.visitors.addRow name equals name, when is date time now. Notice here that because everything was a Python object, we could do things like code completion, because when things stay in one abstraction, it's easier for one part of the system to know about the others. OK, so I've just stuck a couple of things into the form, and you can see that we've recorded those in our database. So we've just built and deployed a database-backed web application with nothing but Python in a very short period of time. Before I get back to sort of discussing the theory of this, I'm going to show you one more thing, which is how to display this data on a page. So I'm going to, well, the first thing I'm going to do is make that data accessible. So on the server, I'm going to define a function, get visitors, and that's going to return all the rows in our table. So I'm just going to search for all the rows in that table. And now in the browser, I'm going to make a card with a data grid on it, and it's going to have a column for the name, which pulls out the name key of the dictionary-shaped objects, when, which pulls out the when key, and I don't really need this third column. I can adjust them and so on. Now, inside this grid is a component called a repeating panel. And this has a property called items, and you give it any iterable Python object, and it goes through and makes an instance of this little chunk of UI for everything in that list. So in the constructor for the page, we can set the items of this repeating panel to the return value of get visitors. Now, when I run this, it's going to go to the server, get a bunch of data, and display it on the page. Excellent. We have some audience participation. So one more thing, actually, before we move on. This is a little bit ugly. You can see we've just called stir on a date time to get some text we can display. Let's make that a little bit nicer. So I'm going to go into the designer. I'm going to go into this little chunk of UI. And I'm going to say, actually, don't give me the default behavior. I'm going to put a component here. And I'm going to say that the text on this label should be so we'll take self.item, which is a row from the visitors table. Remember, same abstraction. This is a Python object all the way from the database to the front end. I'm going to take its when column. And this is, of course, just a Python datetime object. So I can call stir of time on it. So if I run this now, oh, there we go. Num type object has no attribute stir of time. Okay, what have we done here? We have something in there with none. Not quite sure how that got there. Probably UI mesh. There we go. We have much nicer formatting. And again, we've done that not by trying to do some abstraction over data presentation. We've just used Python. Keep the representation the same everywhere, and you don't actually need to know anything new or special to get it done. Also, props to whoever's testing our Unicode support. Well done. It's Python 3. Of course it's got Unicode. So that was all very fun. Let's talk a little bit about what we've just seen. Focus back over here. So that was a great abstraction, right? What have we learned about abstractions? They fail. And this is a whopping great big abstraction. It's an abstraction over the entire web. It's a fiendishly complicated system. There is no way that we can reproduce all of the complexity in a simple Pythonic API. So this is an abstraction that is bound to fail, which means that we need the escape hatches. Let me walk you through a few of the design choices we've made. What about JavaScript? Well, there is a large and mature ecosystem of JavaScript libraries and APIs, and if you're building a web app and you can't use them, then you're going to regret having chosen this abstraction at all. For example, if I want to do some mapping, I'm not going to rebuild mapping in Python. I really want to use the Mapbox API, but that's OK because we built a bridge. From anvil.js.window, import Mapbox, and you can use those JavaScript objects from Python. And my colleague Brooke created this app that shows you how far you can drive, cycle, or walk in a certain amount of time without writing a line of JavaScript. Build the bridge, build the escape hatch. What about text editors? This is something on which subject people have strong opinions. Lots of PyCharm users out there, and the people who are out there who aren't big PyCharm fans, probably big fans of Vim. If something's locked up in a cloud editor, you start to get a little bit nervous. So, of course, we made every application in Anvil a Git repository. You can just clone, edit, commit, push back. Your own computer. That's definitely personal space. You don't want that taken away. More importantly, although Anvil has created this abstraction, we haven't really talked about this yet, but it's an abstraction over the whole concept of DevOps. That was a serverless deployment. I wrote some server-side code, and Anvil took care of spinning up an environment for me. But that abstraction can also break if I want to use local resources. anything from a Raspberry Pi with specific hardware attached I need to be able to access, or a Jupyter notebook on my machine, or a server out there full of GPUs. So we built something called the uplink, which is a library you can pip install and give it a token, and it will connect up to your app. And you can use your code anywhere in the world as if it were part of your app. So here's how an application works normally in Anvil. It's hosted there, and then it's delivered to the browser where your users are. If you use the uplink, you're running code on your own machine that then connects up to Anvil, and you can do everything you can do from the server side of your app. You can make callable functions, you can access your database, you can go to town. And so you can write code like this, for example, on a Raspberry Pi. Anvil Server Connect with a key, make a callable function to show some text. In this case, it's on Pi Maroni's rainbow hat, and make it callable from the client. And here's what that looks like when I did it the other day. Running an application, enter some text, call a function on that Raspberry Pi from the web. So doesn't have to be always have to be hosted. Escape hatch. Yes, okay, fine. Maybe I don't want to use one thing on my computer. I want to do it all on my own computer. Reasonable. Maybe you're working on an oil rig and you don't have a reliable internet connection. Maybe you're working in TV broadcast and the show must go on even if the internet goes down. Maybe you just believe in data sovereignty and you want it on your own computer without anybody else getting in the way. Totally fair. So we created a standalone application server you can pip install, check out your Anvil app, launch the application server, and it will serve your app as a standalone web server. It is, of course, open source. So I hope you've got something out of that stream of examples, and generally the tour of abstractions as a way to think about software. We've learned that abstractions leak, that the details of the system that the abstraction is modeling or of the implementation itself can leak through. And we've learned about pieces of advice like the Zen of Python for building abstractions that are less likely to leak or less painful when they do leak. We've learned that abstractions can fail, where the underlying system permits something to be done and the user needs that thing and the abstraction prevents them. And we've talked about how we can build escape hatches so that the user can get that thing done without losing the benefit of the abstraction we're building. These are design questions. These are questions of taste. It is why the Zen of Python contains deliberately contradictory statements. And like many things to do with taste, a really good way to improve your cooking is to try other people's. So next time you use a framework or you install a library from PyPI, think about the abstraction that it is providing to you. Think about how simple it was to grasp. Think about whether it is leaking. Think about whether it's failed, and if so, what escape hatches were offered to you. And then bring those next time you're writing something for someone else to import. Be that a brand new framework like Anvil, or a function that your colleague's going to call tomorrow. If you are interested in the particular web abstractions that we are building, I am very happy to answer questions, but you can also check them out for yourself at anvil.works. I am Meredydd at anvil.works, and I am very much looking forward to answering your questions. Thank you very much.